Okay guys, welcome to today's lesson in statics. Today we're covering problem number 22 from chapter 4. So number 22 says, for the frame and loading shown, determine the reactions at A and E when alpha equals 30 degrees and angle alpha equals 45 degrees. So as you can see, I've gone ahead and drawn the free body diagram for the figure. I've included the dimensions and all the acting forces currently, as well as the reaction forces at A and E. There's a pin at A, so it'll have both an X and a Y component, and E has a roller component. So it has a normal force to the wall it's pushing up against. Angle alpha is listed here. We're going to first solve for a general case to find E, and then go into specific values of alpha in order to determine the reactions at both E and A. So let's go and get started. First, I'll begin by summing the moments about A. For equilibrium, we know that sum of moments about A must be equal to 0. So this tells us that if we were to sum moments about A, these forces play no part. We have a 20-pound force that is acting clockwise in the clockwise direction around point A. So we have a negative force times its distance, negative moment here, so negative 20, because we're going clockwise for our moment, multiplied by 10 inches, its distance. Here we have a 20-pound force. If we were to move this force's point of location, its point of application, extended along its line of action, you would see that it is also creating a clockwise moment about A. If we were to move this force translated over here, it would also produce clockwise moment. So we can also subtract this force, this 20-pound force, and its distance, its perpendicular distance to point A is only 3 inches. Next, we have to look at the reaction force at E. For E, I'm going to do something a little different. I'm actually going to change up the way this force is displayed. I'm going to extend it out into the diagram itself. So I'll extend the force at E further out, and now it'll have components we're trying to determine. So we have alpha here. This is the same alpha vertical angles here. We have a 90-degree force, perpendicular to this wall here, which means we can draw the components for E. It has a horizontal component as well as a vertical component. So we're drawing this triangle here. It has a 90 here. This is angle alpha right here, which means if this is angle alpha, this must be 90 minus alpha. This is a 90-degree angle here. So as you can see, I have a 90. Bring this into focus real quickly. We have a 90 here, angle alpha here. This angle, therefore, because this is a 90 right here, and this is alpha, this must be 90 minus alpha. This is a 90 here, which means ultimately I'm trying to determine this angle is alpha here. So I have my E in the Y direction, and I have my E component of reaction, E sub x, in the x direction along this axis. So if I extended E further out into EY, going up vertically, and EX going horizontally, I can go ahead and write the reactions, break it down into its components for E. So EY, if this is alpha in this angle, would be the magnitude of E multiplied by the cosine of angle alpha. And EX, the x component of the reaction at E, would be equal to E times the sine of alpha based on this diagram here. So we can now include these forces into our diagram. So we have EY acting vertically here at this point. So we'd have EY, this is creating, if we extend this force up here, it would have a counterclockwise, so it would be positive force. So positive EY. So positive EY multiplied by its horizontal distance. This sticks out 10 inches. This is a further 3, so 13 inches. And then this dimension comes back 8. So this would be 13 minus 8 would be 5 inches. So we have positive EY creating a counterclockwise moment, so it's positive EY times its perpendicular distance from point A, which is 5 inches. And then we have EX. If we remove it further back, we can see it's also creating a counterclockwise moment about point A, so it's also positive. So plus EX times its perpendicular distance, which if we notice, we have a distance of 3 and then 5, so it has a distance of 8 inches from point A. And now this moment we know is equal to 0. So now we can substitute values in and determine what this value is for EY and EX. So negative 20 times 10 would give us negative 200. Negative 20 times 3 would give us negative 60. Plus now EY, we know EY we determined from this diagram, extending this further out and drawing the angles. We know that EY is equal to magnitude E, that reaction, times cosine of alpha, plus EX we know is E times sine of alpha. We cannot forget to include our distances multiplied times EY and EX, so times 5 plus E sine alpha, which is EX, times 8. This is still equal to 0. So now we can solve for E in a general form and then determine the specific numbers when we plug in our angles of 30 degrees and 45 degrees as asked in our problem. So negative 200, negative 60 would make negative 260. And we're going to factor out these terms. So factor out E, pull E out of this term and out of this term. So plus E times 5 cosine of alpha plus 8 sine of alpha equal to 0. We can then move the 260 over, so we'd have E multiplied by 5 cosine of alpha plus 8 sine of alpha equals positive 260. We can then divide both sides by this term, 5 cosine of alpha plus 8 sine of alpha. We divide by this side, we get the same term, 5 cosine of alpha plus 8 sine of alpha. So now we have a general equation that solves for reaction E. We can go ahead and determine what this value is when alpha is 30 degrees and when alpha is 45 degrees. Okay, so when alpha equals 30 degrees, as it does for part A, this tells us that E, reaction E, will be equal to 260 pounds of force divided by 5 cosine of 30 degrees and 8 sine of 30 degrees as well in the denominator. So now going to our calculator, we have 260 divided by, in parentheses, 5 cosine of 30 plus 8 sine of 30. And make sure we're in parentheses when we divide. And this tells us E when alpha is 30, E is equal to 31.2 pounds of force. We can now solve for the reactions at A. We know E is 31.2 pounds of force. Then we can do summation of forces in the x direction equals 0. This tells us that we have a force component. We have EX, AX, and negative 20 pounds acting in this direction. So we're going to have, say, positive AX going to the right. We have 20 pounds going to the left, so subtract that, going in the negative x direction. And we have positive EX plus EX equal to 0. Those are all of our force components acting in the x direction. So now we will keep continuing this line and say ax minus 20 plus ex, which is e times sine of alpha, which shall be e sine of alpha, substitute that in, 31.2 pounds of force multiplied by the sine of 30 degrees equal to 0. This tells us ax is equal to, we'll do negative 20, I should say negative ax plus these values. So ax, we have negative 20 plus our answer we just have, 31.2 times the sine of 30. And that tells us ax minus 4.39 pounds of force equals 0, which tells us ax equals positive 4.39 pounds of force. So here's our answer for when alpha is 30 for reaction ax. Well, now some forces in the y direction. Let's get a line here. Some forces in the y. So looking at the diagram again, our equilibrium condition means it's equal to 0. So looking at our diagram again, we have positive ay acting up. We have negative 20 pounds acting down at point B. And we have a reaction at E sub y, pushing up as well. So we will include all those in our equation. We have positive ay acting up, minus 20 pounds acting down at point B, and then plus ey acting at point E. And this is all equal to 0. So I'll go ahead and move these terms over. I'll say ay equals 20, move 20 over to the side, move ey over, subtract it. So positive 20 minus ey. So now I just need to determine what the value of ey is equal to. Well, I know it's equal to e cosine of alpha. So this is equal to 20 minus e, which I know is 31.2 pounds, times the cosine of 30 degrees. So I have 20 minus 31.2 times cosine of 30 degrees. And this will tell me what my ay force is. So I'm going to say 20 minus 31.2 cosine of 30. And that tells me ay is equal to negative 6.85 pounds of force. If it's negative, that means my reaction that I've drawn in the diagram as it pointing up is incorrect. It's actually acting down. The negative sign simply means we need to flip the direction in which the force is acting. So I'm going to now say that ay is equal to magnitude of 6.85 pounds, but it's acting in the downward direction, so I'll draw a downward arrow. We know ax is positive, it's acting in the positive x direction. It is indeed going to the right. Ay is going down. So we have our reactions for E. We have a reaction ax, as well as our reaction ay. We can now compute the values when alpha is equal to 45 degrees. So we have 30 degrees, and we have alpha is equal to 45 degrees. So first, I will substitute my values into this general equation. For E, I have E equal to 260 divided by 5 cosine now of 45 degrees plus 8 times the sine of 45 degrees again. So we'll get a value for E now. we'll say 260 divided by, in parentheses, 5 cosine of 45 degrees plus 8 sine of 45 degrees. And we'll make sure we're dividing with the denominator in parentheses. So we get a value for E equal to 28.28. We'll round it up to 28.3 pounds of force. Okay. We can now do the same technique for solving for our force in the x to get AX and get our AY reactions, force in the y. So I'll say sum of forces in the x direction equal to 0. Tells me, again, I have the same reaction force equation I have up here. AX minus a 20-pound force plus EX equals 0 to be in equilibrium. This means AX, we move the other components to other parts of the equation to the other side. AX equals 20 minus EX, which equals to 20 minus E sine of alpha. We know E is 28.3 pounds multiplied by the sine of 45 degrees. And this tells us AX will be equal to, just type it in, so we have 20 minus the number we just got, second answer, for a number we just got, times the sine of 45. This tells us AX is equal to 0, which means we have no reaction in the x direction for the pin at A. The pin at A has no x component for a reaction. It has no force it's applying. We'll now determine what summation of forces is for the y direction, to determine what AY is equal to the reaction A in the vertical. So we will say the same equation, AY minus 20 plus EY equals 0, which tells us A sub y, reaction in the y direction for A, equals 20 minus EY, which equals to 20 minus EY is E, this in the frame, E cosine of alpha, which means we have 28.3 times the cosine of 45 degrees. This tells us reaction AY, we have 20 minus 28.3 cosine of 45. So we get a reaction force AY equal to negative 0.01, which tells me that this is also approximately 0. So this is, we'll say it's approximately 0 due to rounding errors. It's not quite 0, which means there is no reaction at A. A has no reaction. The entire reaction force is due to E when alpha equals 45 degrees. So we have a force at E, and we have no force reaction at A for either component, which means A has no reaction at the pin when alpha is 45 degrees, right here, and all the reaction is due to E. And we have our answers for part A and part B. We have 31.2 pounds of force for E when alpha is 30 degrees, 4.9 pounds is right for AX, 6.85 pounds down for AY. There's no reaction at A when alpha is 45 degrees, and E is equal to 28.3 pounds of force. Alright guys, thanks for joining me in another Simple STEM Solution video. Be sure to like and subscribe. Also, if you'd like to support this channel or have particular questions you want answered, be sure to check out my Patreon community via the link in the description below.